4 bonds, 0 lone pairs. Okay, what shape is that? What's the electron geometry? Okay, so the electron geometry, you don't worry about it, or we won't worry about it simply because there's no lone pairs. Once you have lone pairs, you worry about it. But what we are concerned is the overall shape of the molecule, so we'll call that the molecular geometry. Okay, so 4 bonds, 0 lone pairs is tetrahedral. Nicely done, David. Okay. All right, and what is the hybridization of something that's tetrahedral? sp3 hybridization. Okay, excellent job. All right, here you go, tetrahedral. What's the bond angle? It's not something you need to know, but it'd be about 109.5. Okay, 109.5. All right, I'm going to remove one atom here. Okay. So now I have, what do I have here? I have 3 bonds and, what's this? Very good, 3 bonds and 1 lone pair. So what's the electron geometry on that? Okay, it's still tetrahedral, but the molecule isn't tetrahedral. What is it? Okay, you can look at our table here. What will it be? Trigonal pyramidal. Okay. Okay, this is 3 bonds, 1 lone pair. What's the hybridization on this? It's also sp3, just that one of the lone pairs is going to sit on a p orbital. Okay. An example of this, if you remember, was NH3, ammonia. I don't know if you remember that. An example of tetrahedral, there's several, but CH4. Carbon loves 4. In fact, we call it a tetrahedral carbon when you take organic chemistry. Let's do this here. I am going to remove one of the atoms. And now what do I have? I have 2 bonds and how many lone pairs? Okay, 2 bonds and 2 lone pairs. Okay, what is the electron geometry? It's still tetrahedral, except that this is a lone pair. That's a lone pair. So it's still tetrahedral. Okay, but the lone pairs make it what? Okay, this is bent. Okay, so literally the 2 lone pairs do this. Okay, best example of a bent molecule is water. Okay. What is 2 bonds and 2 lone pairs in terms of hybridization? It's also sp3. Okay. Okay, the bond angle for this is 109.5 degrees. What's the bond angle for trigonal pyramidal? Less than it. I'm sure you can find it on the internet, but it's going to be less than 109.5 degrees. What about a bent molecule? Less than that. Okay. Nice job. All right. All right. Now what can we do here? Let's do this here. I'm going to do, that was 4 bonds and 0 lone pairs. Let's do 5 bonds, okay, and 0 lone pairs. Someone want to do this? You want to do this? That's okay. Are you sure? Or you want to take notes? All right, we're going to do 5 bonds and 0 lone pairs. Okay, 5 bonds, 0 lone pairs. Okay, what's the shape of this? Trigonal bipyramidal. Okay, that's going to be the electron pair geometry. And what's the molecular geometry? Same thing. Okay, very good. It's the lone pairs that are going to change the molecular geometry. Bipyramidal. So bond angles, I can see here 90 degrees. Everyone see this? 90. What do you think this would be? 120. We're looking at 90 degrees and 120 in terms of the bond angles. Okay, what's the hybridization on this? sp3d. Okay. So this that has 5 atoms attached to it will be sp3d. All right, let's take one of these out. Now I have, what do I have here? I have 4 bonds and 1 lone pair. This looks like seesaw, am I right? You check your sheet. 4 bonds and 1 lone pair. So if I were to bet, this is seesaw. See the seesaw? Okay, 4 bonds and 1 lone pair. What's that? What's the electron geometry? It's still going to be trigonal bipyramidal. Okay, well, what's the hybridization? It's still going to be sp3d. So what's the molecular geometry? 4 bonds and 1 lone pair. Okay, distorted tetrahedron, also known as seesaw. Okay, so the bond angles are going to get messed up here. Okay, I see a bond angle of 180, but anyways, the bond angles are distorted. Okay, they're no longer nice and neat 90 degrees and 120. Okay, seesaw. All right, let's take out one more. All right, now we have how many bonds and how many lone pairs? 3 bonds and 2 lone pairs. Okay, what hybridization is this? You should know this, Gerardo. It's going to be the same, sp3d. And this is still going to be trigonal bipyramidal. And what is the molecular geometry? Is it listed here? 3 bonds and 2 lone pairs. What is that? 3 bonds and 2 lone pairs is T-shaped. Huh. They call this T-shaped. Okay. So T-shaped. I'm trying to figure out why they call it T-shaped, but anyways. Okay, so this is T-shaped. If I do it like this. Okay, T-shaped. Okay. All right, this is T-shaped. Is the geometry 2 lone pairs. Okay, now let's remove one more. Okay, so now we have 3 bonds and 3 lone. Wait, how many do we have? 2 bonds and 3 lone pairs. Okay, 2 bonds and 3 lone pairs. Okay, it's still trigonal bipyramidal. Okay, but what is the shape now? Okay, linear. So this is 180 degrees. Okay. Linear. And what hybridization is this? sp3d. Okay. All right, let's do 2 or 3 more. This one should be easy. Okay, what's 2 bonds and 0 lone pairs? 2 bonds and 0 lone pairs is also linear. And what's the hybridization of something that's linear? SP. Okay. 2 bonds, 0 lone pairs. Have any examples of anything that's linear? Okay. What molecule is linear? 2 bonds and 0 lone pairs. Say that again. Okay, what's the hybridization again? sp. So how about carbon dioxide? Remember carbon dioxide? Is that a linear molecule? Okay, linear. All right, how about 3 bonds and 0 lone pair? 3 bonds and 0 lone pairs. Okay? 3 bonds and 0 lone pairs. What do you think that's going to be? You want to do this, Maria? 3 bonds and 0 lone pairs? Break. I'm tired. Okay, 3 bonds and 0 lone pairs. What is that? First of all, what's the hybridization of that? This is an sp2 hybridized central atom. 3 bonds and 0 lone pairs. So, yeah. Okay, and very nice. And what is that called? 0 lone pair, so this is called trigonal planar. And what's the molecular geometry? Same, okay? Okay, those have a nice bond angle of 120 degrees. Okay, 120 degrees. Remember an example of something we did that was trigonal planar? Remember anything in anatomy class? You used this a lot, formaldehyde. Okay, that would be something that would be trigonal planar. Okay? Very nice, thank you. Let's see here, that's an sp2. Let's just do a couple more here. Let's do the octahedral, okay? So octahedral will be 6 bonds and 0 lone pairs. 1, 2, 3, 4, 5, 6. Can you do this again? All right, what's 6 bonds and 0 lone pairs? All right, thank you so much. We'll let our classmate Maria make 6 bonds and 0 lone pairs. You guys tell me what that is. Six bonds, 0 lone pairs. 1, 2, 4, 5. Thank you, Maria. All right, 6 bonds, 0 lone pairs. What is the hybridization for that? sp3d. sp3d 2. Very good, sp3d 2. All right, 6 bonds and 0 lone pairs. What's the electron pair geometry? octahedral. And what is the molecular geometry? Same. Okay, what do you think the bond angles are if you were to guess? 90. I see a 90 and maybe a 180. 90 degrees and 180 degrees. Okay. All right, maybe Maria, can you take one out? All right, so now we have 5 bonds. The central atom has 5 bonds with attached and 1 lone pair. Okay, what is the hybridization? Okay, the electron geometry is still going to be octahedral because it didn't change, but what happened is Maria took out 1 atom, and because of that there is, what's there now? Lone pair. So what is 5 bonds and 1 lone pair? It's a square pyramidal. Okay, so we have a bond angle of 90 degrees, but something that's less than 180 degrees. We don't know, but definitely that lone pair messes things up. All right, we have one more thing. Let's take out one more. So now we have 4 bonds and 2 lone pairs. All right. Okay, 4 bonds and 2. Ooh, looks like a nice square. 4 bonds and 2 lone pairs. Okay, what's the hybridization here? Okay. It looks like one of the lone pairs is going to go to D, or one of the other lone pairs will go to D. It's still octahedral, but the 2 lone pairs make it what? Square planar. Okay, and here we have a bond angles, maybe 90 degrees, and then I think it looks like the lone pairs maybe another 180 degrees. Okay, so with the lone pairs, I'm not entirely sure about the bond angles. That's something you do not have to worry about. But if there's 0 lone pairs, the bond angles are nice geometries. But once you have the lone pairs, you see that the geometries can be nice or maybe not so nice. Okay, like bent or seesaw or T-shaped and all that stuff. All right, so yeah, so those are the different types of geometries. This is called VSEPR, by the way, VSEPR. Have you heard of this term? What I've been teaching you since all these weeks is VSEPR. Okay, valence shell electron pair repulsion. Okay. You want me to write it down? Okay. Valence shell electron pair repulsion. That's what all of this is, what we're studying. So table 10.1, table 10.2, make sure you bring that to the test, which is not next Tuesday, but the Tuesday after our Thanksgiving break. All right, thank you, Maria. That was really nice. I appreciate that. Give her a hand here. She did good. Thank you. That actually helped a lot, so thank you again. The last thing I want to teach you guys are something called sigma bonds and pi bonds. Okay, sigma and pi. So if you have a single bond, okay, this is called sigma. And it is an overlap of s orbitals. Okay, do we remember from chapter 7 what an s orbital looks like? Okay, the electron density represents a sphere of electron density. Okay, this is an s orbital. So if you see a single bond, that means it's a constructive overlap of s orbitals. And an s orbital looks like this. An s orbital can house two electrons. Okay, one spin up, the other spin down. We also have something called a pi bond. So if you see a double bond, okay, this is called a pi bond. Okay, and it's actually one pi bond. Okay, and this is an overlap of p orbitals. Do you remember what a p orbital looks like? I got one of them here. This is one of three. Okay, a p orbital looks like a dumbbell. Okay, a dumbbell. Okay, it looks like a dumbbell. We have a dumbbell along the y-axis. We have a dumbbell along the z-axis. Okay, towards you and behind you, and then we have a dumbbell along the x-axis. Okay, so that is a p orbital. Remember, an s orbital is just a sphere of electron density. Okay, remember how the electrons go spin up and spin down. Here, the electrons are housed as spin up, spin up, spin up, and then they pair, spin down, spin down, spin down. Okay, so a double bond is an overlap of one of these p orbitals. Okay, the next thing is a triple bond. Okay, this is an overlap of two pi bonds. Okay, remember these pi bonds are perpendicular to each other. Okay, so I'm going to say it's an overlap of not one, but two of these p orbitals. Alright, so if you see a single bond, think sigma. If you see a double bond, the two p orbitals from this atom and this atom are overlapping. If you see a triple bond, it is two p orbitals from this atom and the other two orbitals, two p's from this atom, are overlapping. Okay. So let's do an example. Okay, our favorite example here is formaldehyde from anatomy class. Okay, so let's do formaldehyde here. Remember formaldehyde, CH2O. Okay, so it's going to have a C double bond O. Okay, with an H. Okay, this is the structure of formaldehyde. Okay, and we have two lone pairs on the oxygen atom. All right, let's first focus on this single bond. This is a single bond. It's also known as sigma. Okay, same thing with this one. It's also known as sigma. And it constitutes an overlap of an s orbital. An s orbital looks like a sphere. So let's see if I can draw this halfway decently for you guys. All right, so we have an s orbital from this one, this hydrogen, and an s orbital from this carbon, and they're overlapping. Okay. Anybody know Dr. Fung? Dr. Fung is an expert on all these orbital stuff. For me, it's like way out there. Okay. So the s orbitals are overlapping. So we have a nice overlap of the s orbitals, which is a sphere. Okay. All right, same thing on this side. This is another single bond, so we'll have the overlap there. Okay, so this is a nice positive constructive overlap of two s orbitals. Okay, an s orbital here, sigma, and two s orbitals here, sigma. S orbital from carbon, s orbital from hydrogen. What about the double bond here? Okay, a double bond is going to be 1s. So we have the s orbital overlap. And what's the other orbital that will overlap? P. Okay. And those are p orbitals that are overlapping. Okay. And this is an overlap of a p orbital. Okay, so let me just go back to our notes here. A double bond is an overlap of is one pi bond plus one sigma bond. Okay, so we have a double bond here, sigma, the overlap of the s, and then the overlap of the p's that are shown in pink. Okay. All right, so that is the pi bond of formaldehyde. Okay, one p orbital overlap. Okay, shown in the pink and blue. All right, let's do one more example here. Okay, let's do hydrocyanic acid. Okay. If we were in the lab last Tuesday, we did this structure. Okay, it is HCN. Okay. So what is the Lewis structure for that? Carbon loves 4. And then to get to 4, we'll do a triple bond here. All right, let's do the diagram one more time here. Okay, this single bond is also known as sigma, and it is the overlap of what type of orbital? S, okay? So there you have that overlap of the sphere, which is the geometry and shape of an s orbital. We also have that same thing here. We have a a triple bond. Okay, notice this triple bond. That's the s orbital with this c and this n. So that's the sigma bond, this sphere and that sphere, overlap of the s orbitals. Okay, what do you think about another overlap? So that's this bond, this double bond actually represents an overlap of one p orbital, and then the triple bond represents an overlap of a second p orbital. So this will have this triple bond will have not one p overlap, but how many p overlaps? 2. Okay, so let's go ahead and draw that. Okay, here's one overlap. And then where's the second one? The second one is going to be perpendicular. Okay. Okay, the second one is going to be perpendicular to the blue. Perpendicular to the blue. So at 90 degrees. The blue and the pink are 90 degrees to each other. And they have the overlap that you see here. So that is a triple bond. So a triple bond is going to be 1 sigma and 2 p or 2 pi overlap. Okay, so we have 1 sigma overlap and then 2 p overlap. So pink is 1 p orbital from carbon, another pink is a p orbital from nitrogen, blue is a p orbital from carbon, blue is a p orbital from nitrogen. The pinks and the blue overlap, they're perpendicular to one another, and then the s orbital, known as sigma, is the s orbital overlap. All right, are there any questions on this? So let's do something a little interesting here. All right, I don't have paper. All right, final thing here for the class. Thank you. All right, let's do something interesting. I want you to figure out the structure of C6H6. This is called benzene. Okay, how many of you have heard of benzene? Okay, what is the structure of benzene? Okay, last thing for the course, and then I will let you go. Okay. All right, C6. How will you arrange 6 carbons and 6 hydrogens? Carbons love to be with carbons, right? 1, 2, 3, 4, 5, 6. Okay, but how will I get 6 hydrogens? One, 2, 3, 4, 5, 6. Okay, what about this carbon, this carbon, this carbon? Something is not right. Can I put a double bond? Can I put a triple bond? What can I do? Okay, what can benzene do? How do I get 6 carbons and 6 hydrogens together? Okay, let me give you a hint. What is this hint? Go ahead. Okay, there'll be double bonds, but Okay, I'll do a double bond. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Is that what you're saying, David? 1, 2, 3, 4. Still, I can't get 6. 1, 2, 3, 4, 5. Wow. Okay, what can you do? How will I get 6 carbons and 6 hydrogens? Actually, the person who discovered this structure got this in his dream. I was reading this book about dreams, and the person who discovered benzene, his name is Kikule. He struggled like we're struggling now, but he got it in his dream. Okay, so maybe you can fall asleep and figure out the structure. But how would you get 6 carbons and 6 hydrogens together? Okay, a circle. Okay, a ring. Okay, it closes in on itself. Okay, so to get 6 carbons and 6 hydrogens, it's going to be carbon, 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 carbon. 1, 2, 3, 4, 5, 6. Okay. So there's your 6 carbons. How will we get to 6 hydrogens? Okay, we put 1 on each. 1, 2, 3, 4, 5, 6. That's good. But how will carbon get 4 then? How will it get 4? A double bond here. Will you get a double bond here? No, because that will be 1, 2, 3, 4, 5. So alternating double bonds. So this is the structure of benzene. Okay. Benzene. Do you see anything else with benzene here? Okay, we can see a resonance with benzene. Okay, the resonance looks like this. You know, I can move this pair of electrons of the double bond here, move that pair of electrons there, and move that pair of electrons there. So the double bonds are delocalized across all 6 carbons. Okay, the double bond is delocalized across all 6 of those carbons. Let's do that really quickly here. One, 2, 3, 4, 5. Okay. Okay, so check out the double bonds here. Okay, the double bonds are shared equally. Okay. Double bond here, double bond here, double bond here. Because of the resonance, they kind of, they buzz around all 6 carbons. They buzz around. So sometimes you'll see, if you take organic chemistry, I think one person is a chemistry major in this room. If we take organic, they actually symbolize a benzene like this. Okay? But because of the resonance, because of the resonance stabilization, they actually can draw benzene like this, a circle. Okay, that just means it's delocalized across all 6 carbon atoms. All right, one final thing about this benzene that I think you may find interesting. We still have, just 2 more minutes or 3 more minutes of class. Okay, we take this benzene molecule. Okay, this is a carbon, this is a carbon, this is a carbon. Carbon 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. Okay, we have our hydrogens, which is fine. Okay, we have a double bond here. Okay, alternating double bonds. Okay, but we know a double bond is an overlap. It is an overlap of 1 sigma and 1 what else? P. 1 P. Okay, so this is a pi bond. So let's draw the overlap here and here. Okay, there's an overlap here and here. Okay, look at this double bond here. There's an overlap here and here. Okay, and then because of the resonance, okay, let's draw the resonance structure. There's also, because of delocalization, there is some double bond character over there as well. And there's some double bond character over here. There's some double bond character over there. Those are these orange dots because of the resonance. So what you see here by the overlap of the p orbitals, what do we see here? I don't think my drawing is doing this justice. Okay, but there is an overlap above the ring and below the ring. Okay, so above the ring there's p overlap, and then below the ring there is p overlap. Okay, above and below the ring there is pi bond overlap. This gives benzene a lot of stability. A lot of stability. Okay. So the overlap is above and below the ring. A lot of people think Alzheimer's disease. It's one of many hypotheses. We don't know if it's true or not. But this benzene is found a lot in your body as part of a protein. And they think this overlap, because you see this overlap can overlap another benzene, and can overlap another benzene, and can overlap another benzene below. So they think that aggregation that is seen in amyloid diseases like Alzheimer's disease may be related to these pi overlaps. The p overlap may contribute in some way to the plaques, amyloid plaques that's seen in individuals with Alzheimer's disease. But this is called, pi bond overlap, because you see this can overlap with another benzene molecule and another benzene molecule. Okay, pretty soon it just starts building up. Okay, so there could be some association with this and Alzheimer's disease as one mechanism.